All right, we're about to dive into a truly beautiful piece of mathematics. It reveals this hidden unity that connects three absolutely massive fields of science. This is a story about one single mathematical object and how it describes three completely different kinds of geometry.
It really does sound like the setup to a bad joke, doesn't it? What could these three fields, which, grew up for over 100 years in their own little worlds, possibly have in common? Well, the answer, as it turns out, is a single, incredibly elegant geometric structure that was hiding in plain sight the entire time. So, to really appreciate this discovery, we first have to wrap our heads around the mystery at its heart. For decades, you had scientists in three totally separate areas trying to solve what they thought were three completely different puzzles. Okay, so in statistics, the big challenge was, how do you measure the distance between two different beliefs, or two probability distributions? Meanwhile, over in quantum physics, they were trying to measure the curvature, sort of the twistiness, in the space of all possible quantum states. And then you had stochastic analysis, the study of random stuff, and they wanted to measure the randomness, or the noise, built into the idea of entropy.
And for the longest time, everybody just assumed these were totally unrelated problems. Statisticians had their tools, like the Fisher metric. Physicists had their Berry curvature. Mathematicians had their own thing for entropy. They all had their own languages, their own toolkits, and were completely unaware they were all just describing shadows of the exact same object.
So what was the first big clue? What was the breakthrough that cracked this century-old case? It was this startling realization that all three fields were, without knowing it, playing on the exact same field, a sphere.
Now, this is where it gets really, really cool. So how do we get to this sphere? Imagine you start in this flat evidence space. Just think of it like a blank sheet of paper. Then you bring in one simple rule from probability. Everything has to add up to 100%. All the probabilities have to sum to 1. Well, that one little rule forces that flat paper to bend into a curved surface. But here's the magic. If you just take the square root of each probability, that curved surface just snaps perfectly into the shape of a sphere. And this right here, this quote just nails the core idea. This isn't some nice little analogy or a metaphor. That fundamental rule of probability, the fact that everything has to sum to 1, is, algebraically speaking, the sphere. The geometry isn't something we just decided to use. It's an absolutely inevitable result of the rules of chance.
Okay, so we've just discovered this hidden sphere where all of our probabilities live. Fantastic. But how do we navigate it? How do we measure things on it? For that, we're going to need a very special tool. And this is the real hero of our story. Let me introduce you to the projector. Don't worry about the formula, P equals psi transpose. Just think of it as a perfect, coordinate-free address. It's like a spotlight that you can point to any single spot on our probability sphere, and it tells you exactly where you are, what your state of belief is, without needing any outside map. But see, the projector only tells us where we are right now. The real star of the show is a mathematical object called a tensor, and we're going to call it Q. Q is the engine that does all the heavy lifting. It's the device that actually measures how our spotlight, our belief, moves and changes as it travels across the surface of that sphere. And this right here is where it all comes together. This single tensor, Q, is the Rosetta Stone. It's the key that translates between our three seemingly separate worlds. You could say it has three different faces.
And here it is. This is the big reveal. When statisticians were measuring distance, what they were actually looking at was the symmetric part of Q. Think of that as its stretching component. When the physicists were measuring that twisty curvature, they were seeing its antisymmetric part, its rotating component. And when the mathematicians were measuring randomness, they were looking at its quadratic variation, which is kind of like its jiggle or its noise. Three different questions, three different perspectives, one single object. They weren't looking at three different things. Not at all. They were all looking at the exact same object, just from three different mathematical points of view. The distance, the twist, the randomness, they were just different facets of one unified structure. So you might be thinking, okay, that's a neat coincidence. But it's so much more than that. This connection is totally unbreakable. It's locked in place by this really powerful mathematical idea called rigidity. This quote just gets right to the heart of it. This beautiful, unified geometry wasn't something mathematicians invented or picked out of a lineup. It was forced into existence by the fundamental rules of probability itself. So,
This is what's known as algebraic rigidity. And what that means, in simple terms, is that once you accept that probabilities have to sum to 1, this tensor Q is the only object of its kind that you can possibly build. There are literally no other options. The laws of algebra themselves demand that this is how distance, curvature, and randomness have to be connected. It couldn't have turned out any other way.
So if this rich geometry is everywhere on our sphere of belief, that leads to a pretty fascinating question. Is there any spot on this sphere where all of that complexity just disappears? A point of perfect calm?
Turns out, yes, there is. It exists at one very special point, the uniform distribution. That's the spot where every single outcome is equally likely. It's the geometric center of the sphere, a point of perfect, beautiful balance.
And at this one spot, something truly amazing happens. The distance metric from statistics, it vanishes. The quantum curvature from physics, it goes to 0. The random noise and entropy, it's gone, completely disappears. All of the complex geometry that defines the entire rest of the sphere just flattens out into nothing. It is a state of perfect symmetry, perfect stillness. So after this whole journey through 3 different fields to find one single sphere and one tensor, what should we really take away from all this? What's the bottom line?
The ultimate lesson here is that the simple, fundamental rules of probability are so much more powerful than we ever give them credit for. They don't just help us count outcomes. They actually give birth to a deep, inescapable geometric reality, a structure that shapes everything from how we reason about data to the very nature of the quantum world.
And that just leaves you with this final, kind of profound thought, right? If the discovery of this one tensor could reveal a hidden unity that nobody saw for a century, it just makes you wonder what other incredible, beautiful connections are out there, waiting just beneath the surface for us to find.